2019, Google was able to solve a complex problem in just over 3 minutes that would have taken IBM Summit, the fastest high-performance supercomputer at the time, over 10,000 years of continuous compute time. There was just one problem. The problem they solved? Completely useless. Why then did this make headlines? Well, it wasn't about the problem itself, rather how it was solved on a quantum computer. This complex machine, using superconducting circuits operating at temperatures near absolute zero, was able to control quantum information long enough to outperform a classical computer. To understand how we got here, we need to go back over 40 years. In 1981, at the MIT Endicott Mansion, a conference unlike any before it was held. It was called the First Conference on the Physics of Computation. Among the attendees were many famous scientists, mathematicians, and physicists of the time. Freeman Dyson, John Wheeler, Ed Fredkin, and Charlie Bennett. These pioneers met to socialize, discuss, and plan for the future of scientific computing. Among the attendees was a physicist who would forever change how we think about computers, Richard Feynman. Feynman may have seemed an unlikely candidate to revolutionize computing. At this point in his career, he was best known and highly regarded for his work in quantum field theory, a highly abstract branch of high-energy physics that describes the interactions inside atomic nuclei. He was a Nobel laureate, a brilliant educator, and had even worked on the Manhattan Project, helping to develop the atomic bomb. But despite these credentials, Feynman was not a computer scientist. Yet, true to his style, he knew how to ask the right questions and come up with big ideas. During his talk at this conference, titled Simulating Physics with Computers, Feynman delivered a line that effectively invented the field of quantum computing on the spot. Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem, because it doesn't look so easy. To the scientists in that room, Feynman's statement about nature not being classical was almost obvious. Quantum mechanics had been around for the better part of a half a century thanks to pioneers like Bohr, Einstein, Schrödinger, and Heisenberg. While early quantum mechanics started as a patchwork of puzzling observations like the double-slit experiment, the photoelectric effect, and the ultraviolet catastrophe, the work of Schrödinger and others turned it into a solid and unified mathematically rigorous theory centered on a master equation, the Schrödinger equation. Schrödinger's approach relied on energy conservation, a concept familiar from classical physics. Just as a ball rolling down a hill trades potential energy for kinetic energy, he reasoned that particles at the quantum scale should follow similar rules. But quantum particles are strange. Experiments like the double-slit experiment show that they interfere like waves even when sent through one by one. This wave-like behavior led Schrödinger to propose the wave function, a mathematical wave describing a particle's probability of being in different states. Schrödinger then posed the simplest problem he could think of using his equation. Imagine a particle, like an electron, confined in a box with infinitely thick walls. If we draw the potential energy diagram for this, it looks like a well, where there's a region with zero potential energy inside the box, but everywhere else has infinite potential energy. If we solve Schrödinger's equation for this scenario, we don't just find one solution. We discover a family of possible states, each with a unique energy level, a tower or ladder of solutions. Not only that, additive combinations of these unique solutions also satisfy the Schrödinger equation. So, for example, if we took the first two states and added them together with some coefficients out in front to weight them, we could create a superposition state, where the particle is a little bit in the zero state and a little bit in the one state at the same time. The same physics that governs this toy particle in a box problem also governs the physics of atoms and molecules. This is why Feynman believed that quantum computers would be best suited to simulate nature. However, while Feynman's talk planted the seed, that seed would remain dormant for several years. In principle, the idea for quantum computing was sound, but early theoretical work in the 80s didn't show anything exceptional. A couple of algorithms for secure communication were invented, but neither of these algorithms lived up to Feynman's promise of fully quantum mechanical simulations of nature. Progress remained slow until the early 90s. In 1992, everything changed. Two theoretical physicists, David Deutsch and Richard Jozsa, showed an algorithm for which quantum computers achieved a true speedup. The problem goes like this. You're given a mathematical function that has two possibilities. One, it's constant, meaning the function always takes the same value. It's either always 0 or always 1. Or 2, the function is balanced. The function always takes the values 0 and 1 with exactly 50% probability. It turns out that, by using a quantum computer, Deutsch and Jozsa were able to show that this problem could be solved in a single iteration, whereas a classical computer would take an increasing amount of time depending on how many inputs the function was allowed to take. This was the result that people were looking for, a real example of a problem which classical algorithms did not solve effectively, but which quantum computers did. However, the next breakthrough was one that took the world by storm. While working at Bell Labs in the early 1990s, a mathematician named Peter Shor came across a paper from a colleague, Daniel Simons. Shor was one of a few scientists appointed to the review team who were in charge of deciding whether Simons' research was accepted to the 1994 Symposium on the Theory of Computing, or STOCK 94. According to Shor, the committee ultimately decided to reject the article from the conference. While Shor did vocalize his disagreement with the decision, he wasn't able to convince the committee of the merit of Simons' work. In Simons' paper, he demonstrated an efficient quantum solution of the following problem. Imagine you have a function, let's call it f of x, that takes in some input, let's say numbers, and gives an output. The trick is that this function is hidden and has a secret pattern. For two specific inputs, let's say x and y, the function always gives the same output if x and y differ by a special number called the secret string, like a password but in binary form. If you know this secret string, you can predict when two different inputs will have the same output. Find the secret string. At first, this problem seems completely useless, and this must have been what many of the reviewers for STOCK 94 thought as well. However, soon after the conference, Shor realized something very important. Really, what Simons' algorithm did was show that quantum computers can find the period of functions. In other words, if a function has a periodic structure, meaning something that repeats over and over again, this algorithm could find what the period of that oscillation was. Separately, another set of mathematicians around the same time had developed some new techniques in number theory and showed that many types of math problems in number theory can be transformed into period-finding problems. Shor took inspiration from both of these developments to develop his algorithm, which has kept his namesake since. He realized that one of the problems that could be reduced into a period-finding problem was the factoring of large numbers. In other words, Shor had found a method to efficiently factor a number into its prime factors. While for small numbers like 15 this may seem trivial, for larger numbers this problem is incredibly difficult. The difficulty of this problem is actually the basis of nearly all modern encryption today. Shor's algorithm was the killer application that brought quantum computing into the limelight. Whereas before it was some kind of curiosity, now quantum computers had serious global implications in cybersecurity, finance, banking, and national security. Once the paper was published, conferences were quickly held to discuss the algorithm. Shor was even questioned by the NSA. It was around this time that experimentalists decided to really start researching the development of quantum computers. Now that killer applications were around, it was time to get to work. But before they could make a quantum computer, there needed to be a framework or some theoretical scaffolding to build around. To actually solve a problem like Shor's algorithm, David DiVincenzo realized that the hypothetical quantum computer would need to meet some basic criteria. He outlined these criteria in what are often referred to now as the DiVincenzo criteria. These are 5 criteria for quantum computers and 2 more if you want to connect them to a network with other quantum computers in some sort of quantum internet, and they're the following. First, you need a scalable physical system with a well-characterized qubit. Second, you need the ability to initialize the state of the qubits into a simple state. Third, you need long relevant quantum coherence times. Fourth, you need a universal set of quantum gates. Fifth, you need a qubit-specific measurement capacity. Sixth, you need the ability to interconvert stationary and flying qubits. And seventh, you need the ability to faithfully transmit flying qubits between specified locations. These criteria laid the ground rules by which experimentalists had to play. If they wanted to accomplish the tall task of building a quantum computer, whatever they built would have to satisfy these criteria. Since we're not going to talk about quantum internet much in this video, let's just focus primarily on the first 5. The first thing DiVincenzo correctly identified was that to make a quantum computer, you need a fundamental base from which to build off. For supercomputers, GPUs, phones, and laptops alike, this is a transistor, which is basically a very, very small electrical switch. Pass a high voltage to the transistor and it's in the 1 state, allowing current to flow through it. Pass a low voltage to the transistor and no current flows, so the transistor is in the 0 state. A transistor represents 1 bit of information. It can take the value 0 or 1 and can be flipped back and forth in computers. In quantum computing, we have something similar. The quantum analog to a transistor is a qubit, or quantum bit. Physically, a qubit can be made in several ways, using superconducting circuits, neutral atoms, trapped ions, or many other methods. In each case, though, the qubits have some commonalities. For all of these physical systems, when you go through the math of quantum mechanics, you get a tower of wave functions with their associated energies. You then make a quantum bit by just focusing in on two of these levels during your experiments, calling one, usually the lower energy one, 0, and the other 1, and using them for computations kind of like a transistor. However, quantum mechanics gives us access to two additional tools. The first of these tools is superposition. Like I mentioned earlier, any two states in our tower can be combined by adding them together to make a new state. This means that unlike our transistor, which functions predominantly like a switch, meaning that it can only be 0 or 1 at any given time, the qubit can be in any arbitrary superposition of both 0 and 1 at the same time. Importantly though, when we measure the qubit's state, the state collapses. This means that the state of the qubit probabilistically takes on either 0 or 1, and the probability of this is determined by the weight which you give each state in the superposition. If your state was 90% 0 and 10% 1, then 90% of the time you measure 0 and 10% of the time you measure 1. The second of the tools we gain access to is quantum entanglement. Entanglement is a special case of superposition and is usually talked about in the context of two different quantum systems interacting with each other. Imagine we have two qubits. Normally, these two qubits will act mostly independently. In other words, changing the state of one qubit should not affect the state of the other. However, we can change this. If we force the two qubits to interact with one another, we can create special superposition states of both qubits which are entangled. For example, we can make a state that looks like this. This is an entangled state, because by measuring the state of qubit A, we instantly know the state of qubit B. For this state, if we measure qubit A to be 0, then we know that qubit B must also be 0. If we measure qubit A to be 1, then qubit B must also be 1. Entanglement is really the workhorse of quantum computing. Since the state of our quantum computer has to collapse at the end of any calculation when we measure it, we really want to be able to funnel most of our probability in our wave function to the right answer. You can think of entanglement as a method of generating interference between qubits, helping us filter out some states and increase the probability of others, which allows us to focus in on the right answer. The second criteria in DiVincenzo's list is a simple one. The qubits must be able to be initialized. If we can't put all of our qubits into a known state to start our computation, then we can't actually do any computations, since any result that we get is completely determined by the starting point. The third of DiVincenzo's criteria is long relevant coherence times. There are two important timescales here, called T1 and T2. T1 is the bit flip time, which is basically the amount of time that it takes for the qubit to spontaneously flip from the 0 to the 1 state. This can happen because of things like thermal noise, noise in control electronics, or spontaneous processes within your qubit itself. T2 is known as the dephasing time, and effectively characterizes how stable the energy of your 0 and your 1 states are. If the 0 state and the 1 state wiggle around a lot in terms of their energy values due to some noise and equipment that changes your potential energy, then you get a shorter T2. In modern-day superconducting quantum computers, these coherence times are on the order of hundreds of microseconds. While this sounds bleak, this is actually an improvement of over 1,000 times since early quantum computing hardware in the early 2000s. Furthermore, improvement to only a few milliseconds should afford us the ability to use a technique known as quantum error correction to drastically improve device performance past this point. DiVincenzo's fourth criteria is that there must be a universal set of quantum gates. Effectively, this means two things. First, we need to be able to do single qubit gates to put our qubits into superposition states. Ideally, we want to be able to control this state very well with high fidelity. 2. We need 2 qubit gates. These 2 qubit gates can entangle 2 qubits together, allowing for interference between states that I mentioned before. The fifth and final requirement is that we must be able to measure the states of the qubits. Since the information from the result of any quantum algorithm is contained in the states of our qubits, meaning whether they're in the 0 or the 1 state, we need to be able to reliably measure which state our qubit is in. Once you have a device that meets all of these criteria, you have a quantum computer that can run calculations. If you want to see an example of one such calculation, I did a video series explaining the deutsch jozsa algorithm in detail, which I recommend watching after this video. I'll link it in the description for those interested. Knowing these criteria, and motivated by Shor's breakthrough, Experimental physicists began the monumental task of building a quantum computer. Before they could run Shor's algorithm, though, they needed to start with something much simpler: a single qubit. This challenge was taken up by David Wineland, a physicist at NIST, whose work with trapped ions and laser cooling made him uniquely suited to pioneer quantum computing hardware. Wineland's journey into quantum computing was not a straight line. In fact, quantum computing wasn't even his primary focus when he started experimenting with trapped ions. Wineland had spent much of his career perfecting techniques for manipulating individual particles. His lab was renowned for their work in ion trapping and laser cooling techniques that allowed atoms to be suspended in space and cooled to nearly absolute zero. These tools were not developed with quantum computing in mind. They were fundamental physics experiments, like building better atomic clocks and sensors. Wineland's goal was precision and control, not computation. But as the 1990s began, whispers about quantum information theory began spreading through the physics community. Wineland, already a leader in controlling single particles, saw the potential for his work to contribute. Around this time, he came across the 1995 paper by Peter Zoller and Ignacio Sirac, which proposed a groundbreaking idea: using trapped ions to perform quantum logic gates. This paper laid out a clear recipe for building a quantum computer using the very tools that Wineland's lab had spent years and decades refining. The path to creating a qubit was not straightforward. Wineland's team faced countless technical hurdles. Quantum computing required unprecedented levels of control, forcing qubits to interact in well-defined ways while somehow avoiding the pesky errors of coherence times. However, his big break came when the team decided to use a beryllium ion as their qubit. The ion's hyperfine energy levels could represent the 0 and 1 states, and lasers could manipulate its state with astonishing precision. But what made their experiment truly groundbreaking was the measurement process. By shining a carefully tuned laser on the ion, they could make it fluoresce if it was in the one state and stay dark if it was in the other. This simple and yet elegant solution allowed them to read out the qubit's state reliably and visually, one of the first demonstrations of a qubit measured in action. When Wineland's team succeeded in building the first qubit in 1995, the response was electric. At conferences like the American Physical Society's March meeting, Wineland presented his results to packed rooms. Theorists were thrilled. This was proof that their ideas could work in the real world. While there were certainly many experimental hurdles to come, this was the proof of concept that was needed to spark an experimental revolution. It proved that quantum information wasn't just a mathematical abstraction, it could be stored, manipulated, and measured in the lab. His achievement, and others, earned him the 2012 Nobel Prize in Physics, shared with Serge Haroche, for their independent breakthroughs in controlling quantum systems. The principles his team demonstrated continue to underpin modern quantum computers, including trapped ion systems used by companies like IonQ and Quantinuum. With this breakthrough serving as motivation, many other research groups decided to work on developing their own qubit systems for a variety of hardware platforms. Techniques were developed in NMR, electron spins, neutral atoms, photonics, and superconducting circuits, just to name a few. While many of these technologies have startup companies backing them right now, the clear frontrunner is superconducting circuits. When you Google a quantum computer, this is most likely what you're going to see. These qubits are based on circuits made of superconducting materials where electrical current can flow without resistance. By the early 1990s, researchers had already shown that it was possible to make superconducting circuits which exhibited quantum behavior, and that we had some degree of control over the state of these systems. But the modern era of superconducting circuits began a few years later. In 1999, Yasunobu Nakamura published a paper demonstrating the first charge qubit, the Cooper pair box. The Cooper pair box used a small superconducting island connected to a large charge reservoir by a Josephson junction. By applying a voltage to the island, they could control the flow of Cooper pairs, pairs of electrons bound by superconductivity, and create a system with two well-defined quantum states. These two states, defined by the presence or absence of an extra Cooper pair on the island, formed the 0 and the 1 states of the qubit for computation. But controlling the Cooper pair box wasn't easy. Early versions of the qubit suffered from short coherence times on the order of only a few nanoseconds, far from what was needed for any practical computation. In the early 2000s, a team at Yale set out to tackle these challenges. They introduced circuit quantum electrodynamics, or CQED, a mathematical formalism based on the Schrödinger equation and a set of approximations for various types of superconducting devices. Circuit QED adapted ideas from cavity QED, which is a similar theory that describes how atoms interact with light inside an optical cavity. Instead of atoms, Yale's approach used superconducting circuits, and instead of optical cavities, they used microwave resonators. This allowed qubits to interact with electromagnetic fields in a highly controlled environment, enabling precise manipulation and measurement. For this reason, superconducting qubits are often referred to as artificial atoms. One of the Yale Group's most important contributions was the invention of the transmon qubit. The transmon was a refinement of the Cooper pair box, designed to be less sensitive to small fluctuations in charge which had plagued earlier designs. By sacrificing some tunability, they achieved much longer coherence times, on the order of tens of microseconds. This development made the transmon a practical and scalable qubit for quantum computing, and is now the go-to design used by companies like IBM and Google. Over the past 20 or so years, this qubit, as well as others, have been refined to the point where coherence times have reached nearly a millisecond. It was using these high coherence transmon qubits that Google was able to achieve its quantum advantage in their 2019 paper. The algorithm they ran was not meant to be useful, but rather to benchmark their Sycamore quantum processor and to show that while useful applications of quantum computing may seem distant, we can exhibit a very high degree of control over the quantum states of devices that we have engineered right now. This paper made the impact it did not because of its implications for now, but because of its implications for the future. If you liked this video, then check out this video on the various types of quantum computers that people are making right now.